All right, so let's talk about simple harmonic motion then. So our task, as in describing any kind of motion in physics, is to find the equation of motion. So something like x of t. That's generally our task. And from there we can take further derivatives and find energy and all these other things. So to do this, we'll pick up from what we just discovered about the projection of the unit circle, and we'll consider a particle moving in uniform circular motion. And that's a very specific set of words that come with a couple equations that you should be at least vaguely familiar with from Physics 1. And remember that its projection models a particle, just like a mass on an ideal spring, in simple harmonic motion. So as this particle travels around the circle, its projection onto the x-axis is just equal to the x component of its position on the circle. So by that I mean x is equal to a cosine theta if we have a circle similar to what we had before, and its radius is a, and we're considering some angle theta here that the particle might be at, some arbitrary position. So if you take cosine of theta, you get adjacent over hypotenuse being a here, right? And so a cosine theta is this here. So hopefully that's a pretty quick exercise for you, because you did it a bunch in probably both previous physics classes. But it's good to make sure that stuff clicks right off the bat. So that's how we get this linear component of circular motion, is we're just taking the x component of that circular motion, so the cosine function. And so, like I said, we have uniform circular motion. It comes with a couple equations. One of those for acceleration, I'll stick with my color scheme from before, is the radial acceleration, so a rad, being equal to omega squared a. So that's nothing I'm deriving here. I'm just pulling it off of maybe an equation sheet that you would have had from your first physics class. So if that's coming out of nowhere for you, and maybe you didn't cover that as explicitly, go back and review that section, and this content will make a lot more sense. So here, again, omega is the particle's angular velocity, and a is the radius of the circle, but it's also the amplitude of the oscillation in simple harmonic motion. And I want you to really think about that. So particles at rest, or starting point and midpoint is there, and it oscillates to a maximum positive amplitude that way, and then comes back this way, and oscillates to a maximum negative amplitude that way. And so you have a being our amplitude of our oscillation, not just the radius of the circle. It's good to make these connections. So you, let's see, I was jumping ahead. So if you look at the x component of the radial acceleration, then all we have is, so a rad x is equal to negative omega squared a cosine theta. Where did that come from? Why is it negative? Well, if I can zoom in enough on this circle here, if you have the particle where it is right here, and you have a radial acceleration like that, make some more room, you have two components of that acceleration, right? And so this would be the x component, so a rad x. And so you have that same angle here, and you have the same cosine going on. So negative omega squared a cosine theta to access that component of the radial acceleration. So why the negative sign? Well, if you look, when x is positive, so it's in somewhere this region here, then the x component of the radial acceleration, this guy here, is pointing to the left. It's pointing in the negative direction. And then likewise, if we were over in this region of the circle, or on that part, the negative amplitude of our oscillation, then the radial acceleration would be like that, and the x component would be pointing in the positive direction. So it always inverses what the position of x is doing. And so because of that, that should signal to you that this acceleration, with it being directly proportional to the displacement and opposite in sign, it confirms the linear restoring force that defines simple harmonic motion. So it acts as our restoring force, right? If you just throw an m for mass in there, F equals ma. So to be more explicit, if we said earlier, go back to white, that x is equal to a cosine theta, well, that's what we have right here. So a rad, x component, is equal to negative omega squared x. And so because F equals ma, right? So that means that our restoring force, in this case, would be m, or negative m omega squared x. And so the key thing that I'm trying to point out here is that x is directly proportional to F, the restoring force. And so you have this proportionality constant right there, but it's not F equals negative m omega squared x cubed, it's just x, right? So let's sum up 3 quick things that we know and see if we can get some useful further definitions out of this simple harmonic motion. So we know that a sub x is equal to negative omega squared x. Just did that. We know F is equal to ma. Just did that also. And you can be explicit and refer to only the x component of that motion if it's a linear oscillation. That's an explicit way of saying that. We also know that the spring constant, the Hooke's law for springs here, is equal to negative kx. So with these 3 equations, go ahead and wake your brain up just a little bit, pause the video, and come up with an expression for omega in terms of just k and m. So just those are the 3 equations. Just do a quick bit of algebra, shouldn't take too long, and come up with a nice expression for omega that involves k and m. So what you should come up with, here, I'll do it with us, I'll do it. So you have these 2 are equal, so you can say ma is equal to negative kx, and then if you move this guy over there, you could say a x over x is equal to negative omega squared, and you can do the same kind of switcheroo here. So you can say a over x is equal to negative k over m. And so then you can sub that in there and say negative omega squared is equal to negative k over m. And so omega is equal to square root of k over m. So that's valid for a body in simple harmonic motion. So that gives us the angular velocity in terms of the spring constant, or the force constant if it's not a spring, it doesn't have to be, and the mass. So since we have a more precise definition for omega, we can go back to another couple equations that, that we had defined in terms of omega, and we can write them out a little bit further. Like, we had frequency, and we said frequency was omega over 2 pi. Well, now we can say frequency is 1 over 2 pi times square root of k over m. Useful for problems. And then likewise period. So we said period's both 1 over frequency, which is 2 pi over omega, which is 2 pi square root of m over k. All right, so let's pause here real quick and just think about this instead of just writing down symbols and not understanding what any of this means. This is physics, not math, so it's important to know that this refers to things in the real world. So let's think about this and see if it makes sense intuitively to our minds. So taking a look at at these two equations that we just wrote down, these two things here. If you have a larger mass, that means you have something with greater inertia. It's oscillating, right? But because it has greater mass, for any given, imagine a spring. So if you have a spring and a smaller mass is attached to it, and then you trade that out for a larger mass, what will happen is the restoring force is the same because that's dependent on the spring, but the acceleration on that larger mass is going to be less because the mass is greater, right? So F equals ma. Right? So if this isn't changing and this gets bigger, then that has to get smaller, right? So if you have a larger mass and all else is equal, like the spring, then it's going to be slower oscillation. It's going to take longer to complete a full cycle. And so that should correspond to a larger t, which is period, and a smaller f, which is frequency. So does it? So larger mass here will produce, since it's in the numerator, a larger t. And a smaller f, well, it's in the numerator there. So if you blow up m, then frequency goes down. So that checks out. That makes sense. Likewise, if you think about the spring, if you're trading out springs and keeping the mass constant, if you trade out for a much stiffer spring, has a much higher spring constant, so K goes from baby K to huge K, right? That would produce a larger restoring force for a given displacement. We would expect that, this F is going up. Here, I'll do new color. So F equals ma. So we're keeping now mass constant, and we're trading up F, and so therefore acceleration should go up as well. It's on the other side of the equal sign. And so it should cause a larger acceleration, and therefore not take as long to complete a full cycle. So smaller t, larger f. So does that check out? So if we increase k, then that's in the denominator, and that produces a smaller t. And if we increase k for frequency, then that produces a larger frequency, which is just what we said. Smaller t, larger f. So definitely make sure and stop and think about these things. If that didn't make sense, or if it's not clicking yet, just go back and rewatch the last 10 minutes or so until this clicks, because it's really useful once you kind of get it all jiving in your head. Okay, so the more observant of you might be dissatisfied so far, because I said, and we started this video, I said our goal was to find this type of an equation, right? An equation of motion. X is a function of time, and time has not really been anywhere in here. Do you see t anywhere? I don't. So where is our x of t? We haven't done anything that we set out to do yet, right? Well, it turns out it's hidden in omega, right? Because omega is d theta dt, right? So there's time aspect to it. It's a rate. It's a rate of angular velocity. So if at t equals 0, the particle makes an angle phi is this guy, with a positive x-axis, then at a later time t, this angle would be theta equals phi, whatever it started at, plus omega t. All right, so this isn't anything you have to memorize. We're going to think it through. So if you start at some position here, right? So this is going to be phi. So you're not exactly starting right where we would usually say the start of our rotation would be. That's phi. Oops. and you're going at some rate, d theta dt, right? So through some amount of time, some slice of time, you've traveled some slice of angle. If you multiply that, right? So you're doing some radians per second, and then you're multiplying seconds by that, right? Radians per second times second. Then what you get is another angle out of it, radians. So at some later time t, you will have traveled, let's say, to here. So this angle would be your phi plus whatever your rate per angle is times the amount of time that it took to get you there. All right. So if that is the explicit statement of our angle per time, that gets the t in there, right? Then what we can say is, instead of saying x is equal to a cosine theta, we now have an expression for theta that's a little bit more explicit based on our starting position and our rate, and we insert our variable t in there. So now we can say that x equals a cosine phi plus omega t. And in fact, you will almost always see it written like this, omega t plus phi. So this equation defines the displacement of a body in simple harmonic motion, where, of course, as we just found up there, omega is equal to k over m, right? So you have a equation of motion in terms of time, in terms of a starting angle, which we call the phase angle, in terms of the amplitude of the oscillation, right? And in terms of the spring or force constant, and in terms of the mass. We got it all going on in one equation. So that's kind of what we set out to have, is a way to describe the motion with one cool equation. And that's for the displacement. So let me, before moving on to taking derivatives of that and finishing out with the velocity and acceleration, let me talk a little bit about this angle phi here. I mentioned that it's called the phase angle. Sometimes it's just referred to as phase. It tells us where the oscillating particle was in its cycle at t equals 0. So where does the oscillation start? So let's take some quick examples here. So if we're saying at t equals 0, then we're wiping out this first term because you're plugging 0 in for t. So what you're considering is the oscillation starts at phi equals something, and you would be plugging in a cosine phi because we were wiping out that first term, right? So if phi is pi over 2, right here, right? That means that it should be midway through its oscillation, and so its amplitude, its position, its x position, should be equal to 0, right? So this is the midway point, this is the origin. So x equals 0, here would be x equals a, and here would be x equals negative a, right? So does it? Well, cosine of pi over 2, 0, and so yes, it does equal 0. So x equals 0 there. How about, let's pick another one. Right here, so at the start, phi is equal to pi. Hopefully you can tell what we're doing there. So if phi equals pi, then you plug in pi here. And so then that's negative 1, right? And so then x equals negative a. So you can see it just completely maps to what the starting x position is of our oscillation. So it's called the phase. It just tells you where it starts. So it doesn't always have to start at where we consider the start of the unit circle to be. You can start anywhere. And so that tells us where it does start. I remember when I was a student, this part here kind of threw me off the first time I saw it, and it just seemed like there's too many angles involved in what was going on, so I'd like to be a little bit explicit with that. All right, so now, like I mentioned, we can take derivatives of this expression here and find velocity of the particle on its oscillating path, and acceleration. So if you take derivative v sub x equals dx dt, which is negative omega a sine omega t plus phi, right? So derivative of cosine, negative sine, omega comes out because we're taking derivative with respect to t. And so that's our velocity. Acceleration, ax equals dv dt, or dvx to be explicit. And so therefore negative omega squared a cosine omega t plus phi. So it goes back to cosine, and another omega comes out. Okay, so we have this expression for acceleration, but didn't we already have an expression for acceleration that I tried to sell you on? Up here we were talking about acceleration, and it didn't look quite like that. It looked like this, right? So negative omega squared x. Well, take a look. If x is this, right? Or more explicitly, if x is this, plug this guy right in there, and you recover what we had expressed before. So ax equals negative omega squared x, because a cosine omega t plus phi. So that's exactly what we said earlier. I said negative omega squared x, which we just ripped right from uniform circular motion. So all over the place you're seeing this this confirmation that linear oscillation can be very easily, very simply mapped to traveling around the unit circle, and considering all of the motion involved with that, and just taking the x components of it. All right.